Hey everybody, welcome back. We're going to go into section 4.3. We're going to learn in this lecture how to find the expected value and variance for continuous random variables. The concept or ideas behind this are very similar to the ones we looked at with the expected value and variance of discrete random variables, with just the process being different because we're dealing with integration with this particular process. So let's kind of get into it. So the expected value for continuous random variable y is defined as the integral over the domain of the PDF. All right, so we still got a little f of y, the PDF here. All right, there's our PDF. But we multiply in an extra y. That's very similar to how we found the expected value of a discrete random variable. We took each discrete random variable y and multiplied it times its probability. The difference there was we had to find all the probabilities if we didn't have a formula for the expected value already, like we did with the specific distributions. But when we were just finding one of a general discrete random distribution, we had to multiply each y value times its probability. Well, with the discrete case, we can do that. For the continuous case, since we're integrating and we can't find exact values for probabilities, we have to integrate over the domain, essentially. And we just multiply that PDF by a little y. All right, so that's how you find expected value. Now, to find the variance, you're going to have to do the following. You need to find the expected value of y squared first, and I am going to require that you find this separately so that there's not a lot of confusing looking work done on your paper. I know in the past a lot of you with the previous ones did the expected value of y minus mu quantity squared and then figured out what that was. Well, you're still going to be dealing with a function and then minus the value each time, so it's better off if you just find expected value y squared first and then subtract that from the expected value of y squared. So do this to find the expected value of y squared. You integrate over that domain, whatever it might be, of little y squared this time times the PDF f of y dy. All right. And so you're just adding in an extra y squared term and multiplying that PDF function by that. And then you can find the variance by doing the good old expected value of y squared minus the expected value of y all squared. I would prefer you do these in different steps. You know, this is technically step 1, step 2, step 3. It makes it easier for me to check off the things that you've done. And I would just appreciate it if you would do that. Okay. Moving on. We've got the next one is a theorem down, which is kind of similar to stuff we saw before as well. It says if g of y is a function of y, then the expected value of g of y is given by the integral again over those things, over the domain, times of g of y times little f of y. So little g of y could represent one of those functions that we've seen when we were trying to find the expected value of a profit, and we had a profit formula, kind of like in that bookstore problem example I did back in chapter 3, and also the one that you had in homework that was very similar to that. It could be representative of that or anything else we might want to have an extra function of. So it's just really multiplying of two functions together and taking the integral. A few other theorems, another things that take place here, just like they did in the other section, or the other chapter, is if c is a constant and we have the following functions, g of y, g sub 1 of y, g sub 2 of y, through g sub k of y, then the following results hold. And this is very similar to some of the theorems or properties we saw with the taking the expected value of in the discrete chapter. So the expected value of a constant is just that constant. All right, you won't get anything different. The expected value of a constant times another function g of y is just equal to pulling that constant out times the expected value of g of y. And if we want to know, last but not least, if we want to know the sum of several functions of g of y over we want to the expected value of several functions of g of y all summed together, then we can separate those and then sum them together. So that's a rule that still applies here. So it's not much different here than what we've seen in the past, so nothing really new here. It's just kind of reiterating the point. Okay. So let's get into, I got about 3 examples here I'm going to do with you. And we're going to find the mean and variance of in each case. So for the first one, I've got that the PDF little f of y is equal to 3/8 y squared over the domain over the interval 0 to 2 inclusive and 0 elsewhere. We do not have to find the CDF here, but we do need to find the expected value. So we're going to start with that. Expected value of y. Remember, the formula on the previous page says it's the integral over the limits negative infinity to infinity of adding an extra y value in there times the PDF f of y. Now, since this has only got a real function defined right here and it's 0 elsewhere, we only really care about the 3/8 y squared part from 0 to 2. So this becomes just the integral from 0 to 2. We don't have to actually go over the whole domain because it's 0 elsewhere. And that's going to be y times 3/8 y squared dy. So it's a y times the little f of y. So let's put that together and make it a little easier. Let's combine terms. So we get 3/8 y cubed dy is really all we're taking the integral of, and this is a pretty nice one. Y cubed, the integral of that would be y to the 4th over 4. We could pull that 1/4 out and multiply it by the 3/8 so that we get 3 over 32 y to the 4th. I will skip some steps on this stuff as much as I can. I won't walk through everything. If you've forgotten some of the steps in doing your integrals, it's a good time to, in this chapter, to revisit those things. And this will be from 0 to 2. Well, that's just going to equal, we don't care, the 0 won't matter to us, but that's going to be 2 to the 4th is 16 times 3 gives me 48 over 32, which is going to equal 1.5. It's almost like they did that on purpose. So there's our expected value. And I guess it'd be 1.5, whatever units we might be talking about, because remember, expected value represents some kind of the average value of our data, whatever our data units might be. Now let's find the expected value of y squared. So again, I'm going to skip the little formula step, but it's the integral from 0 to 2 of y squared this time, multiplied times 3/8 y squared, which is just really equal to the integral from 0 to 2 of 3/8 y to the 4th dy. I forgot my dy there. All right. So when we integrate that, y to the 4th becomes y to the 5th over 5, and 1/5 times 3/8 gives me 3 over 40 times y to the 5th, evaluated from 0 to 2. And 2 to the 5th power is 32 times 3 gives me 96 over 40. And if we simplify that a little further, we get 2.4. I don't care if you put units on the expected value of y squared, because it's not really it's a useful tool in getting to the end point of what we want to do, but it's not the thing we have to have units on. So I will be forgiving on units on that one. If you want to put squared units there, that's fine. The variance of y, again, is just going to be good old expected value of y squared minus expected value of y squared, which will be 2.4 minus 1.5 squared, which ends up giving us 0.15 units squared. So those are the two answers we wanted. So not too bad. Like I said, the integrals in this section are not terrible. A lot of times they're pretty simple integrals. They just want you to get used to the pattern. There's occasions where maybe you have to use some other rules for integration here, such as the integration by parts and things like that. But it doesn't happen often in this book. So let's take a look at a different one. This time we've got the mean and variance we're trying to find for the PDF of 1/2 times 2 minus y. Could just rewrite this as f of y equals 1 minus 1/2 y for 0 less than or equal to y less than or equal to 2, and then 0 elsewhere. I'll just say 0 else. That'll make our integral steps a little shorter. So expected value of y is equal to the integral from 0 to 2 of 1 minus, let me undo that. We got to throw in our extra y times 1 minus 1/2 y dy, which is the integral from 0 to 2 of y minus 1/2 y squared dy, which if we take the integral of the two terms in that integral, we get 1/2 y squared minus y squared becomes y cubed over 3, so that's 1/6 y cubed. Evaluated from 0 to 2. We only care about the 2 because the 0 makes everything go away. And we should get 2 minus 4/3, which gives us a value of 2/3 units for the expected value. All right. The expected value of y squared, similar thing. We're going to 0 to 2. Remember, we're throwing in y squared here. It's 1 minus 1/2 y dy. And here that means we're going to go from 0 to 2, y squared minus 1/2 y cubed. And we integrate that. We get 1/3 y cubed minus 1/2 y cubed is going to become y to the 4th over 4, so this should be 1/8 y to the 4th power. Evaluated from 0 to 2. Again, we only really care about the 2 in this case, thank goodness. We like 0. And that'll give us 8/3 minus 2. And somehow other we get 2/3 there as well for the expected value of y squared. And then we can go ahead and calculate the variance of y, which equals the expected value of y squared minus expected value of y all squared, which equals 2/3 minus 2/3 squared in this case, which is going to equal 2 over 9 units squared. So see, not too bad. I will say this. All PDFs are not exactly the same as the two we've done. I may do a video where there's more than one function like this within your PDF. The only difference between these and those is that you have to also multiply the y into those other functions as well, and integrate over those parts too, because they help add up to the to find your expected value or your variance. So sometimes that can be just an extra add-on feature or added-on thing that you got to deal with. And so I may do a little short video of an example of doing one of those, just so you guys have one. I just need to find one that I'm not going to give to you guys first as a homework exercise or for a test. but I'll try to put one of those out there soon. We're going to do one more like this one here, except we're going to add on some extra things here. All right, so we've got the weekly CPU time used by an accounting firm has the probability density function measured in hours given by 3 over 64 y squared times 4 minus y over the interval of 0 to 4 and 0 elsewhere. Find the expected value and variance of weekly CPU time. So I'm going to call that part A. Part B says the CPU time cost the firm $200 per hour. Find the expected value and variance of the weekly cost of the CPU time. There's B. So we can use A to help us solve B. And then lastly, it asks us, would we expect the weekly cost to exceed $600 very often, and why? I will show you two different ways you can answer that question when we get to it. But let's start with A first. So finding the expected value and variance of the weekly CPU time. So how many hours on average of CPU time is being used according to this? All right. So we'll go on over to the next page to do that. So I've already got the little PDF function written out here, and they want us to find find expected value of y and b of y. So let's find the expected value of y first. Remember, that's going to be the integral, in this case, from 0 to 4, because that's where 3 over 64 y squared times 4 minus y is defined over. So we're going 0 to 4, multiplying, and then that extra y term, 3 over 64 y squared times 4 minus y dy. Putting everything together, that's going to be 3 over 0 to 4, 3 over 64 y cubed times 4 minus y. I'm always cautious when I'm doing this, as should you be, because it's easy, even no matter how good you are, to screw up a multiplication of some terms when you try to jump steps. Try to warn majors about that all the time, and some folks just don't like to listen. That's called being stubborn. Alright, so 3/64 times y cubed times 4 should be equal to 3 over 16 y cubed minus 3/64 y cubed times y should give us 3/64 y to the 4th dy. Now we can actually do the integral on this sucker. 3/16 y to the y cubed becomes 3 over 64 y to the 4th minus 3/64 y to the 4th becomes 3 over 320 y to the 5th, and that's going to be evaluated over 0 to 4, or just really 4, so we got 3/64 times 4 to the 4th minus 3 over 320 4 to the 5th. And when you throw that in your handy dandy calculator, you get 2.4 hours. And I guess that's weekly hours, but we could just say 2.4 hours. All right. Now we can find the expected value of y squared. Okay. So I'm going to integrate in 0 to 4, and I will skip a step this time because I'm going to multiply in y squared, right? It's the only thing that should change from my previous, from finding the expected value y, is that value right there. Instead of being y squared, it should become y to the 4th. So I'm going to write that as 3/64 y to the 4th. You can skip that step as long as it's obvious that you've done that, but be careful. It's easy to make a mistake doing these things. Integrate 0 to 4. That's going to be, again, 3/16, this time y to the 4th, minus 3 over 64 y to the 5th dy. Now we integrate this sucker, and we get y to the fourth becomes y to the fifth over 5, so that becomes 3 over 80 times y to the fifth minus we get y to the fifth becomes y to the sixth over 6, and 6 times 64, so that fraction will reduce to 1 over 128. You don't have to reduce it, but I did. 0 to 4, and that's gonna just equal. I'm gonna skip the step where I plug the 4 in, but you know how to do that, so it should be 6.4 for the expected value of y squared. So lastly, we need to find the variance because we'll need that in the future. And the variance in this case is going to be, again, expected value of y squared minus expected value of y all squared. And I'm just going to plug in here. We get 6.4 from the expected value of y squared minus 2.4 quantity squared, which somehow turns out to be 0.64, which I find to be rather interesting. Being the fact that the expected value of y squared was 6.4, that might just be circumstantial. Anyway, there we go. We've got our 3 parts that we need. So now we can move on to part B, and let's remind ourselves about what part B was asking. It says find the CPU time costs, or the CPU time cost the firm $200 per hour, so that's important. So that's really saying 200 times y, because remember y was the CPU time they measured in hours. And it says find the expected value and variance of the weekly cost for the CPU time. So since capital Y really here represents the number of the hours overall, and it's $200 per hour, what we're really going to be doing here is the following. So this is part B. We're really finding the expected value of 200 times y, which, remember, since 200 is just a constant, means we can pull that out. It's 200 times the expected value of y, which means that this is equal to 200 times, and the expected value of y from the previous page was 2.4 hours on average, so this ends up being $480 per week, essentially. But $480 is really all we need to put there. Okay. The expected value of y squared is very similar, or of this weekly cost is really just 200 y all squared, which means we can go ahead and square that stuff inside, and that gives us 40,000 when we square 200 times y squared. Again, we can pull the constant out front, times the expected value of y squared. Here's why it was important for us to find y squared, and why I keep harping on that, because sometimes that value comes up in problems. So having that separately will help you answer some other questions from time to time. And so that's really 40,000. And I believe that, if I'm not mistaken, let me look here, yes, expected value of y squared was 6.4. So the expected value of the weekly cost squared is going to be 256,000. All right, so we're going to need that here in a minute. This we wanted. This we need to get to as an ends to our means to our ends, or whatever they say. So now we need to find the variance of 200y. Well, that's just going to be us taking in the expected value of 200y. We do need that, but not yet. Expected value of 200y squared minus the expected value of 200y all squared. It's going to equal 256,000 minus 480 squared, which gives us $25,600 squared. All right, and we needed every bit of that. Okay. I'm going to go ahead and find the standard deviation because I want it to help me answer part C. Even though it didn't ask for it here, I think it's kind of important that we bring that out. So I'm going to find sigma, which is the square root of the variance of 200y in this case. And that's just the square root of 25,600, which means that the standard deviation is back down to single units of money, and we get $160. All right, flat. Okay. So I'm going to use that here in a minute to answer part C. So let's go back and read what part C is asking us. So part C says, would you expect the weekly cost to exceed $600 very often? And then asks why do you think yes or no? On these questions, a yes or no is never sufficient enough. You're majors at this point. Give me a yes or no answer is pretty much worthless. So don't do that. Most of you have been pretty good about not doing that, so that's been good. You guys have been a pretty good group. I know I don't praise you enough, but you've been pretty good. So part C, there's two ways that you could answer this question. One idea is if we use the empirical rule. If we use the idea, or the concept, if you will, of the empirical rule. Now, we don't know if this data is normal or not, but this is something we can kind of always backtrack to. Remember, we always, in the empirical rule, we went from the mean, we went out one standard deviation unit with 68% of the data fit in there, our possible outcomes fit in there. If you went out two standard deviation units, 95% fit there, and anything beyond two standard deviations was like 99.7% of the data or more. Well, unusual to consider something to be not something you'd normally see. Usually that happens beyond two standard deviation units from the mean. So if you're fairly still close to the mean, that's a good thing. That means that's not necessarily, depends on your outlook, I guess, on what the data's saying. In this case, if we're still somewhere between 1 and 2 standard deviation units away from the mean, between that, not beyond 2, then that outcome is likely to be seen. It's not impossible. It becomes more, not impossible, but improbable once we get beyond that marker of 2 standard deviation units away from the mean, if you think about it. Draw that down here. So think about this. Say we zeroed it out and the mean was 0, so you go 1 standard deviation below and above, 2 below, 2 above. Anything that falls in here is something that you could potentially see occur, and with fair regularity. Of course, you're going to see things happen more closely related to 0 there in this case than out to 2, but the stuff between 0 and 2 away is possible. Those are possible to see. Anything that falls out here is going to be considered to be unusual, or not very likely to be seen, or very improbable. That's because once you get out there, think about what you got left over. If from 0 to 2, below and above is 95%. So if all this is 95% of the data, right, then there's only 2.5% below and above. So that's like 0.025. So anything below 5% of being a probability below 5% is considered unusual. Anything higher than that's considered, we could possibly see that. So that's something to keep in mind here. So I guess what I'm trying to say is, if we use the idea of the empirical rule, anything more than, say, more than 2 standard units, and I'm talking about standard deviation units here, is considered unusual, and we would not expect to see those things. All right, we would not expect to see that. I just want to just say we would not expect to see such things. Note the following about our particular weekly cost, the expected value of our weekly cost, and the standard deviation we just calculated. So note that if we take our mean plus 1 standard deviation unit, that's $480. So this will be like, this is 480 down here. Plus 160 was our standard deviation, so we're going up 1 standard deviation unit. That's already at $640. If I go up another standard deviation unit, in other words 2 units, 2 times sigma, that's 480 plus 2 times 160, which I believe, and you can double check me on this, is 800. And it should be at 160 plus 640 plus 160 is 800, so this is 800. So realistically, we wouldn't expect to see anything in excess of $800 on average, but something in the excess of 640 is a possibility, because there's there's $160 worth of space between 640 and 800, so there's a good possibility that would happen there. All right. Since we see, so I guess a good answer to this is since 640 is only 1 standard deviation, or 1 standard unit away from the mean. Then say since $604 is only 1 standard deviation unit away from the mean, then seeing a value in excess of 600 is not unusual. And that'd probably be a good answer to something like that, or some kind of wording such as that. All right, and your proof of it is, what you found in part B helped you answer this question. All right, I kind of wanted to harp on this because we haven't done much of that, but the empirical rule and Chebyshev's theorem, those concepts can come up and help you answer questions a lot of times when you're not sure how to answer the question, especially when it pertains like, would you expect to see this kind of thing happen very often, or how often do you think this would happen? Those kind of questions, most likely they're going to be answered like one of these. The other way you could have answered this question was actually to use probability in integration. So we could have also answered this question this way. Let's see. Let me add another page here. Add one. So we're going to call this part C the alternate answer solution. So what we could have done is said, well, what's the probability that our weekly cost, which was represented by 200y in part B, is actually greater than 600? We could have asked ourselves that question right there. Well, if we do a little solving here, then this is the probability that y is greater than 3. And remember, our PDF, little f of y, was over the domain of, or over the y intervals from 0 to 4. So we're really going to do now is set up an integral where we find the probability from 3 to 4 of that 3 over 64 y squared times 4 minus y dy. And we get that probability. That probability will help us determine whether seeing $600 or more would be unusual. All right. So I'm going to just do the integration real quick. So it's the integral from 3 to 4 of 3/16 y squared minus 3 over 64 y cubed dy, which equals, let's see, that's going to be 1/16 y cubed minus, let's see, 3 over 64 north, it should be 3 over 256 y to the 4th. Evaluated from 3 to 4. We need to actually plug both of those in, so we got 1 over 16 times 4 cubed minus 3 over 256 y 4 to the 4th minus that stuff with 3 plugged in. And when we do all that, we end up getting, once you simplify that, you should get roughly 0.2617 as the probability. And since 0.2617 is greater than 0.05, 0.05, remember, is kind of the measure where I mentioned a minute ago of being unusual. Anything below 0.05 would definitely be unusual, but this probability is bigger than 0.05, then we should expect to see values in excess of 600 per week. Doesn't mean we'll get them, but we can expect them. And you might could even word that we should expect from time to time to see values in excess of $600 or something like that. And that is pretty much it. Either way you answer this question, I'm fine with it. Both of these are legitimate answers for the question like this. So keep that in mind. Other than that, that's all I've got for you this go round. I hope everybody's doing well, and talk to you guys next time. Bye.